Today I want to talk to you about a French mathematician named Michel Rolle. Now Michel Rolle has a very interesting theorem, and that theorem says that if we have a continuous function on some closed interval, so from some a to some b, and that function happens to be differentiable on the open interval, so it may not have a derivative defined at the endpoints, but it has a derivative defined everywhere in the middle. So if the derivative is defined everywhere in the middle, and it's continuous throughout the entire closed interval, then there is at least, and there might be multiple, but there is at least one point where the derivative is equal to 0. So we are guaranteed not only a critical number, but specifically a critical number that for which the derivative is equal to 0. Now recall, some of these critical points, like in this graph here, the critical point exists, but the derivative is not defined there. So ultimately we have this thing, and in these 2 points, the derivative, or the slope of the tangent line, is 0. So the value of the derivative is 0. So again, you can have multiple points, but the big conclusion is really, and I forgot the last piece, f of a has to equal f of b. Now, that's an interesting piece. We're going to find we can actually do even a little better than that as we go along, but ultimately what you can do a lot of times is you can take a function over a whole space, and as long as you find 2 random points, like these 2 random points equal each other here, so we find that Rolle's theorem applies even in this range, or even in this tiny sliver. So you can kind of move your window as you need to. Anyway, the point being is that Rolle's theorem is a very powerful theorem that allows us to get interesting understandings of the functions that we're dealing with. However, we have to be careful. Remember the requirements. The requirements are that it has to be continuous on the closed interval, and it has to be differentiable on the open interval. And differentiability is usually the one sticking point you're going to have. So notice in this particular case, I have a function, and it seems to be continuous on the entire closed interval. And it does actually have a maximum, but if we were to take the slope of the tangent lines, they would be going up, 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 and then break and immediately come down. And that's because the derivative is not defined there. You know, you think of those as limits, you're going to have one that's always positive, one that's always negative, and they're not going to go to 0. In fact, the limit's going to go up to positive infinity and then come up from negative infinity. So just remember that for Rolle's theorem to apply, you have to have all the requirements satisfied. So over here, we want to say, why does Rolle's theorem not apply? Well, in the case of the absolute value of x minus 1 in the range 0 to 2, well, if I'm graphing that, that's a shifted absolute value. And on 0 to 2, this thing's clearly continuous, and the function value at 0 and the function value at 2 are both 1. So it satisfies all the requirements except for differentiability. The derivative is not defined here at x equals 1, so Rolle's theorem does not apply. Similarly, when we take a look at tangent of x over 2 from 0 to 2 pi, well, tangent of 0 is 0, and tangent of 2 pi, or tangent of 2 pi over 2, so tangent of pi, is also 0. So why wouldn't Rolle's theorem apply? Because tangent has a derivative, tangent is continuous, or is it? Well, if you take a look at x equals pi, so tangent of pi over 2, sine of pi over 2 over cosine of pi over 2. And that doesn't exist. So you have a graph that looks like that. So while it is continuous on this open interval and it is continuous on this open interval, it's not continuous on the whole interval. So Rolle's theorem does not apply. So be careful before just saying, well, Rolle's theorem applies, I've got this, that, and the other. You have to satisfy the requirements. And finally, what we're going to do is we're going to take a look at an example where we know it satisfies the requirements, and we're going to use that information to determine where f prime would be equal to 0. Notice that this guarantees it exists, but we haven't shown how to figure out where that value is. So I have f of x equals x times the square root of x plus 1. What I know is that the square root of x plus 1 is continuous from -1 to positive infinity, and x is continuous everywhere. So I know that at least from -1 to infinity, and then this is differentiable, this function will be differentiable on -1 to infinity, but only in the open interval. But again, differentiable in the open interval is fine, continuous in the closed interval is required. And we may not even need to be there, but so the first thing I need to do is find the x-intercepts. So why am I doing this? Well, the reason I'm doing this is because I have to figure out points where the function is equal. F of a equals f of b. So if I know the points where the function output is 0, well then I'm guaranteed equality. So looking at this, f of x is equal to 0 when x is 0 or x is -1. See, if I plug in 0 here, the whole thing's 0. If I plug in -1 here, the whole thing's 0. So those are my two intercept points, which tells me that there's some number somewhere where f prime of c is equal to 0, and that number has to be between -1 and 0. Or there has to be one between these two. There could be one outside that interval, but we're not worried about that. So then we take the derivative, which by the product rule is the square root of x plus 1 plus x over 2 square root of x plus 1. If we get a common denominator, that's going to become x plus 1 over x plus 1 plus, or sorry, square root of x plus 1 over x2 x square root of x plus 1. So if I do a 2, I get that, which gives me 3x plus 2 over 2 square root of x plus 1. Why am I doing? Well, I'm doing this because what we're trying to do is we're trying to find x values that make the derivative equal to 0. So when x is -2/3, we see that the numerator is 0. By plugging it in, the 3's cancel, -2 plus 2 is 0. And then on bottom, -2/3 plus 1 is still in the domain. You don't have to worry about it being a square root of a negative number. So that tells me that when x is -2/3, f prime at -2/3 is 0. And so your answers would be, these are your x-intercepts, and this is some value. And notice that -2/3 is between -1 and 0 on the number line.